Hey everyone, and welcome. Today we're going to talk about something so common we honestly take it for granted, but it powers just about everything that moves in our world, the electric motor. Yeah, they're everywhere, in your house, your car, all over our industries. But as you're about to see, this simple idea of just making something spin, well, it gets incredibly complex and, honestly, pretty fascinating.
So let's start off with a little bit of a puzzle. Picture this. You've got a maglev train that literally floats on its tracks, a pump that's working thousands of feet under the ocean, and a robotic arm that's precise enough to perform surgery. I mean, these are three completely different worlds, right? Three totally unique engineering problems. But the answer to what they have in common? It's that at their core, they are all powered by a very, very specialized electric motor.
Okay, so let's get into this. You see, the term electric motor isn't just one thing. It's a huge, massive category. A good way to think about it is like the word vehicle. I mean, a bicycle is a vehicle and a rocket is a vehicle. But you'd never use a bike to go to the moon, right? It's exactly the same with motors. For every single unique challenge out there, some brilliant engineer has designed a specialized motor to get the job done.
So let's start with one of the most extreme environments you can possibly imagine, deep underwater. How in the world do you run a high-powered electric motor when it's completely submerged, under crushing pressure for years and years at a time? Well, this is where the submersible motor comes in.
And you can just see right here, these things are two fundamentally different beasts. A regular motor that you might see in a workshop, it's air-cooled, sitting safely above ground. But a submersible motor, it is designed from the inside out to live in liquid. It's not just waterproofed. Its whole system for cooling and its mechanical structure actually depend on being submerged.
So how is this even possible? Well, it's a completely sealed, watertight unit with really robust seals and O-rings. The housing itself is made of special materials that won't corrode. And inside, it's actually filled with oil or water. Now that liquid does two things. It cools the motor, but it also equalizes the immense pressure from the outside. Even the insulation on the internal wires is a special water-resistant polymer. It's a true engineering marvel, just built for survival.
All right, let's switch gears to a completely different challenge. Forget surviving the deep sea for a second. How do you create motion that is perfectly precise and perfectly repeatable down to a fraction of a single degree? This is absolutely essential for things like 3D printers, CNC machines, and modern robotics.
And one of the coolest answers to that question is the stepper motor. The genius of it is right there in the name. It moves in these discrete, totally predictable steps. And because each step is a fixed angle, the controller knows the motor's exact position just by counting how many steps it's told it to take. You don't even need a complex sensor for feedback, which is amazing.
Let's walk through how this works. It's really clever. So first up, we send power to coil A. That creates a magnetic field, and a rotor in the middle just snaps right into alignment. Right now, it's stable and it's holding its position. Okay, now for the magic. We turn off the power to coil A and instantly turn on the power to coil B. The magnetic field shifts and the rotor immediately turns, in this case, a precise 60 degrees, to align with that new field. That's one step. Simple as that. And then you just repeat the process. Turn off B, turn on C. The rotor takes another perfect 60-degree step. Now imagine cycling through these coils thousands of times a second. What you get is motion that is incredibly exact. This is the secret behind the flawless movements of a 3D printer's nozzle or a flatbed scanner.
But you know, steppers aren't the only game in town when you need precision. For jobs that need higher speeds and more torque, we have what are called servo motors. And here we see a classic engineering trade-off. On one side, you have AC servos. They run on alternating current, they're quieter, and they need way less maintenance because they don't have brushes that wear out. On the other side are the simpler DC servos. They're powered by direct current, but their brushes can create electronic noise, and yeah, they need to be serviced regularly.
So far, pretty much everything we've talked about has been about rotation, about spinning. But what if you need incredibly powerful, high-speed motion in a perfectly straight line? Well, for that, you have to basically unroll the motor and lay it flat.
You know, the pioneer of this technology, a guy named Eric Lathwaite, had this fantastic way of describing his creation. He called it a magnetic river. And that just perfectly captures this idea of a flowing, invisible force that carries things along with it, with no physical contact at all. So the principle behind it is both really simple and kind of profound. Imagine taking a normal round motor, slicing it open, and just laying it out flat. Instead of a magnetic field that spins around, you now have a magnetic field that sweeps down this flat track. When that moving field passes over a conductive plate, like the one on the bottom of a train, it creates currents that generate their own opposing magnetic field.
The two fields then repel each other, pushing the plate and whatever it's attached to forward.
And the real-world applications for this are just incredible. This is the tech that lets maglev trains fly down a track at hundreds of miles an hour. It's what silently catapults fighter jets off of an aircraft carrier. It's even the secret behind that thrilling, gut-wrenching launch on a modern roller coaster. I mean, this is motion completely redefined.
Okay, so we've seen motors built to survive the deep sea, motors for microscopic precision, and motors for pure straight-line speed. And this brings us to probably the most important concept in all of motor design. There's no free lunch. Every single choice is a trade-off.
So let's take a look inside two different motors here. On the left is something called a switched reluctance motor, and on the right is the stepper motor we just talked about. Just notice how different they look inside. The shapes, the number of teeth on the parts. These aren't just random designs. Every single detail is a deliberate choice that balances things like how much it costs to make, how complex the controls are, how much torque it has, and how smoothly it runs. So, what's the key takeaway from all this? At the end of the day, there is no single best motor. There is only the best motor for a specific job. An engineer is always asking these questions. Do I need raw power, or do I need delicate control? Does this thing need to last for decades untouched, or can it be easily serviced? And the big one, is cost more important than pure performance?
And this all leads us to a final thought for the future. You see, the electric motor isn't some solved problem from 100 years ago. It's a technology that is constantly evolving to meet brand new demands. As we push into deeper oceans, build smaller and smaller robots, and demand more efficiency from everything, engineers will be right there, designing the next generation of these hidden marvels that silently power our world. It makes you wonder, what will they look like next?